Good day and welcome to this GCMS training. My name is Lucky Mokwena. I'm the Divisional Manager for the GCMS lab that forms part of the mass spectrometry unit that is at the Central Analytical Facility, which is based in Stellenbosch, at the Stellenbosch University. First, I will talk about the sample prep techniques, and then also talk about the instrumentation based on focusing mostly on GCMS. The reason for wanting to talk first about the sample prep is because most people tend to forget the importance of sample prep techniques. They only want to focus mostly on the instrument, bearing in mind that the instrument can only give the result based on what has been fed into the system. So I will talk about some of the sample prep when we go to that part. As mentioned in my introduction, there are some important things that one needs to consider when doing the before analysis when it comes to sample prep. The sample matrix is very important. When we talk of sample matrix, we're referring to the question that is it based, what type of a sample? Is it a solid sample? Is it a liquid sample? Or is it a gas phase sample? The reason why that is important, then it can determine which sample prep you will perform. And also, it's important to know the miscibility of the sample. Is your sample soluble in an organic solvent, or is it an inorganic solvent? If it's an organic solvent, is it whatever the polarity is, or is it polar, or is it non-polar? Of course, then that will help determine which solvent to use. And also, what are the compounds of interest? When it comes to volatiles, what type of volatiles are you talking about? Terpenes? Are you talking about alcohols? Are you talking about esters? Because it could help you determine what type of sample, whether you do liquid extraction, whether you will do solid phase extraction, or you do headspace. Are you talking about pHs? So you might have to consider doing QueChERS. You might have considered doing solid phase extraction based on whether you're working with a liquid or a solid. And if it's a contaminant, what type of contaminant are you talking about? Is it sulfur-based contaminant, or is it chlorine contaminant? For example, maybe trichloroanisole, or is it phenolics, or which is halophenols? See, sometimes when we want to do sample analysis, we just get carried away and we forget to pause a little bit to ask those relevant questions. I know there are some clients who they come to you, they present to you with a problem, they just want you to find solution. But if you don't ask those questions, you will not be able to give the client the right solution, because you might think you've given them the right solution only to find that you're giving them something different. So spend a little bit of time with the client discussing what they want, and also what is their explanation of contaminant. And also, I've heard in the past people speak of when they talk of trichloroanisole, they'll tell you, for instance, maybe the wine is corked. So if the wine is corked, it can mean a lot of things. It does not necessarily mean it's trichloroanisole. It could be that maybe there's some TTN, or you've got maybe vitispirin in there, which gives a corked smell in the wine, but people think it is trichloroanisole. Also, the volatility of your compounds of interest. How volatile are your compounds of interest? Why is that important? It is important because if your compounds of interest are very volatile, so you might find that maybe you have to keep them in a cooler temperature for you to not to lose your volatiles, or not to lose your compound of interest because of their volatility, or maybe also the stability of your sample, or the compound of interest. If your sample is very unstable, you might have to keep it in a cooler condition, or maybe do your preparation in a cooler environment. Or if your compounds of interest are very volatile, you might have to prepare your samples maybe in small batches. Especially if your lab is not cool enough, your aircon is not performing well, so maybe you can prepare all your samples and keep some of them in the fridge up until they're ready for injection. Maybe depending also on the length of the method. You might have to just add on your samples maybe in an hourly period, for instance. Maybe your first 8 samples, and then the next 8 before you go home. And also, the other thing that's important, the concentration range that you're working with. Are you working with milligram per liter, which is ppm? I call it above trace. You can call something else. And also, are you working a trace analysis, which for me it's a ppb, between 1 ppb and 1,000 ppb. That's trace for me. You can call it something else. For me, ultra trace is anything between I would say in the ppt range, or maybe from 1 ppt to 1,000 ppt, or even lower. You can also regard it as ultra trace below ppt level. Why is that important? It is important because because you're working with ppms, and maybe from 1 ppm to 100 ppm, you might have to maybe dilute your sample instead of working at those higher range, because most of the instruments are very sensitive at above trace in ppm. So maybe you might even have to reduce your concentration level of the standard, because for some instrument, depending on the compound, you might lose linearity when you work at higher concentrations. When you work at trace in the ppb level and ultra trace, you can start treating them similarly, because you might have to do injection in a single ion mode, same which we're going to talk about later, or you can use MRM, sometimes call it SRM. We'll talk about later when we go into the instrumentation part. Also, your injection mode that you can use is splitless injection, of which when you're doing ppm range, splitless might be too high. You might have obviously definitely have to use a split injection. We'll also explain what is the difference between split and splitless, and also there's an example how to calculate when you're doing a split ratio, how much of the injection you're making. Now, here, there's been a lot that one has to take to consider now. So what now with all these questions? One may ask. Now, where do we go from here? All those questions that one has to think about, which I believe is very, very crucial, is very important. So I will go now into the next slides, talk about some few sample prep techniques. As mentioned earlier about some sample prep techniques, we'll have a look at liquid extraction, solid phase extraction, solid liquid extraction, Headspace, and QueChERS, how they are used and where they are used. Now let's continue with the sample prep. First, we're going to talk about the liquid extraction. Liquid extraction, if some of you who've done chemistry from level 1 until you finish, you'll remember when we were still starting, we were doing some extraction where we were shaking, having muscles, and if you think well, we were just doing it because we were fascinated. We didn't really know what we were doing and how important that is. If you look at the top left corner, you'll see there's a separating funnel there and some colors. I guess it brings up some memory and then not also giving away your age, of course. Liquid extraction involves a water immiscible solvent like your hexane or ether or dichloromethane or chloroform. That extracts are analyzed from the aqueous solution. Aqueous meaning mostly watery medium, and then you shake and then you release the pressure. You shake, release the pressure, and then you can depending on what you're using. If you're working with dichloromethane, for instance, your dichloromethane will be at the bottom, and then the water at the top. If you're using ether, for instance, your ether will be at the top and your water medium at the bottom. So you can just release depending on where your organic solvent says. And then also it is important also to consider the polarity of your compounds of interest. I always say it is important to match the polarity of your compounds of interest with the polarity of the solvent. If you're working with polar compounds, you obviously have to use a polar solvent to extract them, because if you use a non-polar solvent, you're not going to get the polarity, the polar compounds in it. It makes sense to consider the polarity. And also, just briefly now, again, in more details of a sample. As I say, you've got a sample and you've got an organic solvent, then you're gonna you add a certain volume of your organic solvent, and you water the samples. For a few seconds, maybe 30 seconds to a minute. Then from there on, you put it in an ultrasonic bath, or you can use a shaker, so that your compound of interest goes into the organic phase. And then if you're using the separating funnels, it's always important to remember to just release the pressure every now and then from the top stopper. And after sonication, you centrifuge your sample, you separate your organic solvent, you put it aside. So it's always a good idea to do a multi extract. So you might extract 2 to 3 times. And then from when you're done, you pull all those extracts together. Because if you do multi-extracts, then you make sure that all your compounds of interest are in the polar solvent. Because the mistake that we sometimes make, we think if I'm extracting with 10 ml of the sample, I have to add the whole 10 ml at once. But it might be a good idea to first add maybe 3 ml, and you put it aside, and another 3 ml aside, and lastly 4 ml to get your 10 ml, and then you can extract all your compounds of interest. And then also it is important to add a little bit of sodium sulfate to dry your organic solvent, because the water that might be retained is not good for your GC, or it might also affect the sensitivity of your compounds. And then what you can also do, depending on what you're working with, what you call maybe the concentration range that you're working in, you might have to concentrate your sample with nitrogen, either completely and you consider another solvent, or maybe you can reconsider up to a certain level. Maybe you had 2 ml or 1 ml or 2 ml, you can concentrate up to 100 microliter or maybe 200 microliter, and then put it in an insert, and then put it in a GC vial, and then your samples is ready for injection. Solid phase extraction is a sample prep technique by which compounds that are dissolved on or suspended on a liquid matrix are extracted according to their physical and chemical properties. If you look at the top right corner there, you'll see that there's a manifold, and on the manifold right at the top, those are SPE, and the SPE has got what we call a frit. In that frit, that's where your compounds of interest will be absorbed, and then you can dissolve it or elute it with an organic solvent, bearing in mind the polarity of your compounds of interest. And so basically, it's always important that when you get the SPE, you have to condition it with, for instance, methanol. You can first clean up, maybe with the eluting solvent to make sure that's clean, and then methanol, and after methanol you add water. After adding water, after equilibrating, you load your sample. After loading a sample, you can wash the impurities with a buffer, depending on the one you're working with, and then you elute with an organic solvent. SPE can be used. You can either use it as a sample prep technique or as a sample cleanup. If you're using it as a sample cleanup, so you can put your samples onto the SPE, and you can collect the eluent, and then the eluent you can take it further. Subject to another sample prep, you have to. But if you're using it as a sample prep, you let your liquid go through. You don't collect it as yet, and then after all the liquid has gone through and you've washed the impurities, now you can put a clean vial at the bottom, and then you can collect with a organic solvent or solvent interest, and then also you can do on derivatization on the SPE in terms of thiols and other analysis where the derivatizing agent is got added into the aqueous sample, and then you elute it, and then from there it absorbed on the SPE, and you elute it. So there's a lot of things that you can use it for. Also bear in mind there are different polarities of the SPE, so which you can also find a lot of information out there from the supplier of this SPE, or one can check on the internet. There's a lot of information about that. Also now, like you did with a liquid there, when you're doing liquid extraction, you had if you had a water phase in your sample, in your organic phase, if you had some water, you can dry them with sodium sulfate, and you can also, as mentioned earlier, you can evaporate with nitrogen to concentrate your sample either to completion or to a certain volume. You can transfer it in a vial and you can inject, or you can also from there on you can do derivatization if you offline derivatization if you're not doing online derivatization. So there's a lot of opportunity for that. Solid liquid extraction. What is solid liquid extraction? Solid liquid extraction involves where the solid is transferred from a solid phase to a liquid phase. A simple example of the solid liquid extraction will be when you brew coffee, which involves the mixing of the solid coffee ground with water, or a tea when you from the tea bags to the water, boiling water. Another example is in the herbal industry, or in the other various food preparation industries, when a vegetable matrix necessitates extraction for further processing. It's obviously of fundamental importance to ensure that a high degree of extraction efficiency is reached, that the extract is not oxidized, and so on. So maybe the time that it takes to do the extraction will be important there. And also, many lab processes requires solid phase extraction as a preliminary phase for the preparation of sample. For example, as happens in analysis of environmental contaminants in vegetable, the operation of solid liquid extraction must guarantee that all the analytes are retrieved completely and that they are in no way degraded during the extraction process. There is currently in the food industry, there are essentially 3 different solid liquid extraction techniques, which is maceration, percolation, and critical fluid extraction, which we will go further into it, because this was just to introduce to you some extraction techniques. Headspace is one of the widely used form of sample prep techniques nowadays because of the potential that it possesses. Advantages: you can work with minute samples. If you don't have a lot of sample, you don't have to use a lot of solvents if you're doing direct SPME. And we'll talk also about some SPME techniques, like for instance, also mentioned on fiber derivatization. And then SPSE, we're not going to talk a lot about that, but what I can say about SPSE stands for stereo bar software extraction. From what I can remember, it was developed by Pat Sandra, and they had a student, from what I remember, that they were doing extraction for volatile compounds, and then when they did extraction or injectional instrument, they either lost compound of interest, or the sensitivity was too low, and then the student was panicking, and then Pat Sandra asked, what are the chances that the compound of interest might be retained on the stereo bar, or on the magnetic stereo? And then they took that magnetic stereo, did another solvent, and then they spin in the solvent, and they took the solvent and they injected, and then they're starting to see peaks, and then they said, okay, right, they can now maybe coat that stereo bar with different tube, for instance, to see if they can change the polarity of that stereo bar to attract the compounds of interest. Thermal desorption, it makes use of 10x, use 10x. And then if you've got a thermal desorption unit, you can also use a Stera bar in there. So when your compounds of interest are attracted on the Stera bar, you can just put it in a thermal desorption unit and then just run and then flush that with your carrier gas, and then you get your compounds onto the column. And then there's different types of solid phase of SPME, like your PDMS, your DVB, carboxane, that's a pink fiber, PDMS is red fiber, and then you've got PDMS, DVB, carboxane. You get different types of colors there. It has to do with the polarity of the compounds of interest, and also the fiber, the polarity. It's important to match the polarity of the sample and the polarity of the fiber. SPME, there's a chemistry of the headspace. It's important to understand that there is an equilibrium between the volatile compounds and the headspace coating on the fiber. What happens is that the compounds of interest get adsorbed on the fiber, and then after some time, the fiber gets inserted into the injection port, and then the volatile gets dissolved into the column through the liner by flow with a helium that can be used as a carrier gas, or let me say the carrier gas. It's always mentioned that the extraction time, the salt addition, and dissolution time are optimized when developing in a method. The extraction time, it's important that one needs to optimize it, because you might find that for some compounds 10 minutes extraction is enough, some 20 or some 30. Addition of the salt of the salt, 10% salt or 20% salt or 30%, because when you add salt, the salt helps for the compounds of interest to move more into the headspace where they are very much comfortable if they are comfortable in the sample. And then also the salt addition also helps to protect the fiber from swelling. And the dissolution time, the most used dissolution time is it's 1 minute or 2 minutes. But if you've got if you don't have what they call the fiber conditioning station, if you're not doing automated SPME, and then one might leave the fiber for longer than maybe 10-20 minutes in the injection port, because the time after a minute or two, the compounds are already into the column, and then all what's left now for that remainder of the times for the fiber to be cleaned in the injection port. And the sample time could also be optimized. Sample time means how much time do you take to absorb your compounds for the sample, and also the sample volume. How much volume do you need for that extraction? As mentioned earlier on when I was talking about the SPE, it is also important with the SPME to condition the fiber before using it, because if one does not condition it, one might, when you run on the GC, you might see peaks, especially if you've got an FID, see peaks and you think maybe it's a peak from the compounds, especially if you're working with unknown, only to find that it's the compound that one is seeing is coming from the bleeding on the stationary phase of the fiber. So it is important to condition the fiber before using it. And as when one purchases the SPME, in the box which they are inserted, there's also information how to condition and precondition the fiber, and what to do and what not to do. And I always remember when you condition the fiber to open the split vent on the instrument to reduce impurities from the fiber entering the column, and also to ramp up the column after fiber conditioning, and then make sure that all those compounds which will have been retained, trapped on the column, are flushed out. Also, never ever use a glass and a liner with a glass wool, because that will definitely damage the coating on the stationary face of the fiber. And then when working with SPMEs, bearing in mind that you're already working with very minute sample, because it's on the column of the fiber, the liner that one has to use has to be a narrow bow liner. Anything between 0.75 to 1 millimeter. Sometimes you can even go to 2 millimeter ID, internal ID for the liner. Also, one of the things that one must never do, you must never ever soak any SPME in the chlorinated solvent like dichloromethane or chloroform, because they will definitely strip the tip of the fiber. The fiber will definitely swell and strip. And then, so addition of the salt might help to reduce the swelling. So the question one might ask, what if I have to analyze for chlorinated compounds in my sample of interest? So one might have to, you definitely have to make sure that your sample is more in a watery media. Maybe one can first dissolve the sample in methanol, and then, or maybe in acetone to break down the chloroforms, the chlorinated solvent, and then also obviously maybe I'll add a little more water in that, because the most important is not to have more of the chlorinated compounds in there. As mentioned earlier about when I was introducing the SPME, I mentioned that one can do derivatization. You can do direct derivatization in a sample matrix. One can do the derivatization in the SPME fiber coating, or derivatization in the GC injection port. The direct derivatization in the sample means that the fiber get inside the liquid phase, where there's a derivatizing agent, and then the compounds with the derivative get absorbed on the fiber, and then you get the retried and get injected on the GC. If one is doing the on fiber in the sample derivatization in the SPME fiber coating, that is the on fiber. So what you can do the simultaneous derivatization and extraction, or a derivatization following extraction. So the simultaneous derivatization and extraction, it's everything together. The derivatizing agent get absorbed on the fiber, and then from there on in the sample. So like one thing, when one working, for instance, with thiols, where you use OPB FPR, where you extract maybe first a sample from your wine with an organic solvent like a mixture of ether and pentane, and then you dry your sample completely. You add sodium chloride solution, and then from there, let me replace. Okay, you do the you put a sample. You adjust the pH, you add the derivatizing agent in that sample, and then you vortex, and then after vortexing it, you sonicate, you centrifuge, and you take the organic solvent, and then you take the organic solvent, you dry it completely with nitrogen, and then you add organic, you get sodium chloride solution, typically 20% of sodium chloride solution, and then you take that vial. You can either do automated SPME, or you can do manual SPME. So whatever, you take that fiber, you put it on the headspace of the line of the vial, and then the derivatization happen on that fiber on the headspace, and then you inject and you get your peaks. Next sample prep technique that I want to talk about is the QueChERS: quick, easy, cheap, effective, rugged, and safe. This form of sample prep, it is a solid phase extraction method for detection of pesticides in food. It's used a lot, mostly in the food industry for pesticide analysis. The reagents used depend on the type of sample to be analyzed. Briefly, how the QueChERS work: you've got your sample, you weigh the sample, typically 10 gram or 5 gram or more, depending on what you're working with, and then you add the organic solvent and the internal solvent. You can also add water in there to have your sample to talk, because if you just add organic solvent on its own, you might not get the compounds out, and then you agitate. And then from there, now after that, you add your sodium chloride solution, sodium chloride and magnesium sulfate in the buffering and adjust the pH, and also you agitate, and then you can take that liquid. You can run, you can concentrate up to a certain level, and then you can do a lot of other sample prep from there if it has to, and then you can when you've got that liquid, you do GC injection, you can do liquid injection. But also, for instance, just maybe a brief example, maybe like when we're analyzing for acrylamide in potato chips, where we weighed the potato chips, and then we added water, and then we added acetonitrile. And then we found that we were having a lot of interferences because of the fat that was in the potato chip. So we introduced the hexane, because then the hexane will trap all the fat, and then the acrylamide, that pesticide, will go into the acetonitrile. By introducing the hexane, we also improve the sensitivity of the sample prep, because sometimes people think when we speak of sensitivity, the only thing sensitivity is instrument related. Now they forget that the instrument can only give you what you've injected. Before you want to speak of the sensitivity of the instrument, one needs to make sure that you've already exhausted everything you possibly can on your sample prep. Now, a little bit more about derivatization. Remember, I mentioned about on-fiber derivatization when I was talking about the SPME, and then also on the SPE. Okay, just a little bit more about derivatization. Derivatization is the process by which a compound is chemically changed during producing a new compound that has properties more amenable to a particular analytical method. Some samples analyzed by GC require derivatization in order to make them suitable for analysis. Like, for instance, compounds that have poor volatility or poor thermal stability, or that can be absorbed in the injector, will inhibit non-reproducible peak areas, heights, and shapes. Compounds that respond poorly on the specific detector may need to be tagged with a different functional group. Before doing derivatization, it is important that one needs to understand and know before choosing a derivatizing agent. A good derivatizing agent and procedure should be: it produces the desired chemical modification of the compound of interest, and the reproducible, efficient, and non-hazardous for the GC and the GC column. Just maybe to stop there, because for instance, one may say that one never ever should. For instance, when you doing a derivatization, when you derivatize, for instance, with any TMS, trimethylacylane, you should never ever inject those samples in a polar column, because you will definitely damage the column. So when you're doing acylation, you have to use a non-polar column. There are all three basic types of derivatizing reaction: silylation, acylation, and alkylation. Silylating agents react with compounds containing active hydrogens, like for instance in phenols, the H from the OH is what they call the active hydrogen, and or when you're working with amines or amino acids, for instance. These reagents are the most common type used in GC. Isolating reagents react with highly polar functions such as amino acids or carbohydrates like your sugars. Alkylating reagents target active groups on amines and acidic hydroxyl group. Multiple derivatives, sometimes one might do multiple derivatizing agents, like for instance when you're working with androsterone, testosterone. In this multi-step derivative procedure, the use of the other types of reagents such as oxime, hydrazone, methylation, and cyclic derivatives may be necessary. If one considers the example of this derivatization reaction of androsterone using TMSI with a trimethylsilane and methoxyamine, so what normally one will do is you'll extract your compound of interest from the sample using whatever sample prep, organic solvent or whatever from the water medium or whatever sample. And from there, the first thing that you do is you add the methoxyamine. What the methoxyamine will do, it will go and sit in the oxygen of the ketone, and then it take where the oxygen of the acyl group will be, and then it makes that stable. And then you add TMS with the temperature heat up, and then the TMS will sit on the hydrogen of that OH up there. And then obviously this compound will now have a new molecular weight. Say for example, the molecular weight of the compound before derivatization was, for example, 102. If you add 102, you add, most importantly, it's the TMS which you add that, and the methoxyamine is the one that will change the molecular weight. So it's important that when you look on the GCMS that you won't see the initial molecular weight, the formula whether you see, you're going to see an additional with the TMS. It's also important to bear that in mind. If one look at this chromatogram here, if one look at the top chromatogram, the one which is not enhanced, where you see the first peak it says 2, and then 1, and then 3, and then 4, 3, 5, and 6. That chromatogram is the chromatogram where there was not a derivatized, the sample was not derivatized, and you can see also look at the retention times and how the peak look like. That sample you get very poor sensitivity on the sample from the sample when you do GC analysis. Now, and then also now after derivatizing, because it was derivatizing with TMS, look at what happened now with the with the peak number 1. The peak number 1 is well resolved from peak number 2, and then look at the order now. It's where it goes from 1 to 7 as compared to what it was at the top, where you were seeing 2. The first peak was peak number 2, and then peak number 1, and then you had peak 4 coming before peak number 3. And then obviously 5 and 6. And look at peak number 7, which just after 20 minutes, which was not we were not seeing before derivatizing. Now one can see the benefit of the derivatizing this compounds with TMS and methoxyamine, and then obviously it makes sense that you will get a very good sensitivity because of that. If one look at this slide explains the slide number 15 in 15 and 14 in more detail, which is a multi-step derivatization. Derivation can substantially improve the chromatographic results, as seen in this example of derivatization of androstenedione in that figure where I showed you earlier that you could see now with derivatizing the peak were higher and sharper as well, also including the order in which the compounds were coming. And that androstenedione contains a hydroxyl group and a carbonyl group, and that exhibits poor peak shape and poor separation if analyzed and derivatized by GCMS as previously shown. Using simulation, the active hydrogen on the OH or SH and the NH groups can be replaced. Since a trimethyl imidazole, you can use any silylating agent or like a BSTFA, MSTFA is a strong silylate donor. It will react directly with the hydroxyl group on the androstenedione molecule, creating a TMS derivative. Now, the molecule creating a TMS derivative, because androstenedione also contains a carbonyl group, another derivative is needed to improve the chromatographic peak separation, which is that's why the methoxamine direct with the carbonyl group for forming an oxime derivative. And then it can not only improve chromatographic performance but also alter the GC separation. Now next we come to the instrumentation part. The GCMS chromatograph consists of the injection port, and you've got the injection port, you've got the GC column, and you've got the detection part. And that in injection port, one will talk about the injection mode, where you talk of the split or splitless injection or PTV program temperature vaporizer, and also the type of splitless injection can be the pulse split or splitless, and some manufacturer call it this pulse split or splitless. They call it the program vaporization, if I'm not wrong. Sorry, I beg your pardon. They call it a pressure surge. What happens there when you do a pulse splitless or pressure surge is one has got what you call operating head pressure. Say for instance, when your instrument is standing still, and then before you do the injection, your pressure is say for instance 50 kPa. So if you do a pressure surge or pulse splitless, you increase the pressure, the operating head pressure, maybe up to 200 or 300 kPa for a few minutes, and before the injection, the pressure could get built up to that, and then when the pressure has been reached and stabilized, and then the injection happens, and then you can keep that for a minute or two. 2 minutes is sufficient, and after 2 minutes, the pressure will drop down to that operating head pressure that you had of 50 or 60 in the beginning, right through the injection of your compound. That also helps to improve the sensitivity of your method now based on the instrument. Remember when I talked about the sample earlier on, I said one has to first try and improve the sensitivity from the sample prep before one wants to see the sensitivity also on from the instrument. They go hand in hand, but first with the sample and then on the instrument. And then also under the engineering, you see with the scepter. The scepter it's there to help your system to stay under pressure, because if you don't have the scepter, or if the scepter has got a hole, then you can start losing the compounds of interest, and that will affect your sensitivity. And the ferrule is there to keep your column intact into the GC on both the injector and also on the detector side, whether using FID, whether using NPD, whether using MSD, you still need that ferrule. A graphite ferrules can be used on the injector and on the detector if you're using FID. But if you're using MSD, never ever use a graphite ferrule on the transfer line. The transfer line is the union between the gas chromatograph and the mass spec. There you have to use a Vespel graphite. Normally 85% Vespel 15% graphite is the, I beg your pardon. Yes, Vespel graphite is the best one to use, because if you use a Vespel on the MSD, because they are very brittle, and then as you tighten the column, the nut, and then they will start breaking into the column, and then you lose the seal. And also you've got the liner. The liner is used for focusing. When you do injection, if you put the liner, which means your compounds goes from the liner into the column. If you don't have the liner, the hole is sort of too big into the injection port, and then you lose sensitivity, and you don't have focusing. And then also part of the column, as I said earlier, after the injection port, now you've got the column. You've got to use polar, mid-polar, and non-polar column. So we're not going to talk about the chemistry of the column here, because it's beyond the scope of this training, because it can be long. But we can talk a little bit more about polar, because the polar column normally goes up to 250 degrees Celsius. This will be your inner works column, your stabil works column, depending on which supplier you're using, or your DB works, ZB works, stabil works. And then they use a lot for volatile compounds, like mostly in wine. If you're doing your alcohols and your esters, this type of column work much better. And the mid-polar column normally used a lot when one is analyzing your fatty acids, methyl esters. And non-polar column, these are very versatile, because you can go up to depending on what column, you can go up to 300. Some can go up to 350 degrees Celsius or 325 degrees Celsius, because they are stabilized with a siloxane, if my memory serves me well. And then the GCMS, you've got the GCMS, which is MSD as mass electric detector. You've got a single quad, the triple quad, and the time of flight. The single quad and the triple quad do pretty much the same work. The only difference is that with the triple quad you can do what you call MS or MRM, which you can't do with a single quad. But you can still operate as a triple quad as a single quad, but you can't operate a single quad as a triple quad, because you only with a single quad you can only do full scan and the SIM, which is single ion monitoring. Which with a triple quad you can do SIM, you can do SRM, you can do full scan, and sometimes you can also operate those instruments in both SIM scans, or where you don't lose the full scan possibility. Because if you only do SIM, you can't do a library search, because that's a disadvantage of that. But if you do full scan, you can do a library search. But if you do full scan, you might find that it affects your sensitivity when you do quantification, especially if you're working at lower concentration. That's why you need a single ion monitoring. So it's a balancing act, in fact, to try and do both SIM scan, because if you do SIM scan, you all in all you're going to lose a little bit of sensitivity, because it's a balancing act. It's also important to choose the correct qualifier ion if you're working with a SIM and a quantifier ion, both for SIM, and also the right transition, just to make sure that one does not have, you don't get interferences. Sometimes one might have to choose a lesser qualifier ion if you've got interfering ions. You don't always have to use the higher ion, or you don't always have to use the base peak when you qualify and quantify. We'll talk about that later. What is the qualifier and quantifier? We'll talk about later. Under the column, just briefly, as I mentioned earlier, with the non-polar column, they are made of polysiloxanes. when one sees the, for instance, HP1 or HP5, it tells you the number of the siloxane in that, and that it can actually it tells you about the polarity of that column, the number of polysiloxanes in it. Also, for instance, if you've got a DB5 or ZB5 or HP5, it means that 5 means 5% of the diphenyl substituent of polysiloxane was added into that column. So what they do is they start normally from a polar column, and then they start introducing those polysiloxanes to go to a non-polar column. And as mentioned earlier on, the midpolar column are mostly made up of cyanopropyl phenol or diphenyl groups, and these are used mostly for fatty acids analysis, FAMEs, and also the polar column, which are made up of polyethylene glycol, like your HP5, I beg your pardon, HPFAP, ZBFAP, the inner works and the DB works. As I said, the maximum they can go, the temperature they can go is 250 degrees Celsius. If you start going up about 250, 260, you'll start melting and then start bleeding into the detector. Splitless injection under the injection mode or injection technique. When one does the splitless injection, everything that you inject goes into the column, and then you get higher peaks, and then it increases the sensitivity of your chromatography. And one uses SPME when you're working with trace and ultra trace. But anyway, a good injection helps to fulfill the following. It allows the column's optimum separation efficiency to be achieved. It allows small but representative amounts of sample to be injected accurately and reproducibly. The sample composition must not be changed during the injection. Was not sample based on differences in boiling point, polarity control of the sample should occur. Now, as I mentioned, the splitless injection is used mostly for trace and ultra trace analysis, where the majority of the sample is injected into the column. The perfect flow can also be introduced normally at 30 or 50 ml per minute for 1 or 2 minutes, and after this, the split line vent line is opened, and the bottom of the septa is quickly flushed with carrier gas. Flushing the septa with the carrier gas helps to clean the septa, and also to keep sample that will be absorbed on the bottom of the septa from getting into GCMS and then through the injector, and then creating ghost peaks of you. And the other thing with splitless, as I said, if you're working in PPTs and lower PPBs, splitless injection will work much better. I always say, some people say, but how do I differentiate between a split and a splitless? It is simple. So if you think in a case where your peak was very, very minute, very, very small, and then if you're doing split, if your peak was very, very small and you start doing splitless, you can enhance that peak. Now with a split injection, a portion of the sample is introduced into the column while the rest is allowed to pass or is lost through the split vent. An example of injection, in fact, before we go to the example, a split injection is an electronic way of diluting a sample. So in case you run a sample in a splitless mode and then your peaks are very, very high and you don't have time to dilute the sample manually, what you can do, one can start introducing what we call a split, maybe a split of 5:1 or 10:1 or 20:1 or 50:1 or even 100:1 split. But the disadvantage of high split, running a high split, it means because you're using a lot of carrier gas and working with helium, for instance, helium is expensive, so it's a very good, it's a balancing act when one working with a split. But anyway, an example of a split rate injection is saying that a split ratio of 1:50. If you run, it means that 50 parts of the sample is injected, but only one part of that goes onto the column. If the concentration rate of an analyte is, for instance, 25 microgram of the analyte per microliter, and 1 microliter is injected into the column, and the split vent is opened before the 1 microliter injection is made, this means that a mass, one can go through the calculation there. It basically means that it's as if 25 out of 50 dilution has been made, but the time required is only the software flip of the switch and not manual. Now that a dynamic dilution has been made without actually adding solvent and actually making a dilution, split engine helps to reduce the sample size to an amount that is compatible with the sample capacity of the column, and also it shortens the retention time of the sample vapor in the liner, resulting in a small injection plug. So what happens there, and then the peak, when you do a split injection, if your peaks were high, they will come down. If you had a peaks which are overlapping, they will be separated. For instance, if you running a sample and then you're seeing, because I've always asked a question in the interview, if I always ask a question, I give, for instance, a chromatogram, I say, okay, if you would use a chromatogram, I give you with a lot of peaks, which are not resolved baseline. I ask a question, is that one peak or is that more than one peak? And then any answer, it can be one peak, it can be 2 peaks. And I say, but how will you determine if it's one or if it's more than one peak? And then the answer will be either dilute the sample and run again with a splitless, or run a split. So what I'll do, I'll introduce split. If that peak is got resolved and then nicely peak shape, then it's one. But if you're seeing more than 1 or 2, 3 peaks, and then they will be resolved, and from there on, the next thing will be now to dilute the sample further. So that's how I always explain to people the importance of understanding the split and split injection, especially for students. That question that I asked earlier on, if it's one peak, it can give a lot of answers. It helps to understand if you know what is the difference between a split and a splitless injection. Now, the next thing is for us to talk about some basic components of the mass of a MS. If one look at this picture that we have here, you look at the green box at the bottom. We've got the sample inlet. The sample will have come from the column after separation has happened, because now here MS now it's separating based on the mass charge to ratio, and then from there through the column, the sample goes into the compound goes into the ion source. Ion source, that's where ionization happen. Ionization, you can have EI, electronic ionization. You can have CI, chemical ionization, which is an induced ionization. It's a softer form of ionization. It's used mostly for esters and alcohol, especially if one is not seeing a molecular ion. And then one can use a chemical ionization, because as I said, you induce your ionization, and you set the condition yourself of ionization to happen. And and then you got the mass analyzer, where the mass sorting happens. They are sorted based to mass charge to ratio, and then from there you've got the detection, and then from detection, the ions get detected, goes into the mass, or you get a mass spectrum, and everything happens in a vacuum, which you call a vacuum envelope on the MSD.
The new thermoscientific TSQ8000 high-performance GC triple quadrupole mass spectrometer offers innovative technology that is both reliable and easy to use. The TSQ8000 GCMS system offers unstoppable productivity for challenging matrices with uncompromised MS-MS simplicity, automated SRM development, and maximum uptime with vent-free source removal. The TSQ8000 system features the Thermo Scientific Extractobrite source cartridge, the first ever source on a GC triple quad that can be removed under vacuum. All parts that need routine service are contained in the source cartridge, including the patented RF lens, which protects the ion guide and quadrupoles from matrix buildup. The Extractobrite source also features a repeller designed to overcome matrix burn when it eventually forms. The Extractobrite source insertion tool makes it easy to insert the source into the instrument without breaking vacuum. The TSQ8000 dual heater design delivers heat directly to the ion volume, the lens stack, and RF lens to prevent matrix buildup where ion burn would occur. The source, lens stack, and ion guide are designed so that the negative effects of matrix buildup are minimized. This means you'll have high sensitivity and precision on the first injection, but also on the 1000th injection. Ions are first generated by electron impact in the dual filament source. The TSQ8000 system features an S-shaped ion guide, eliminating the direct path of neutral molecules to the detector, reducing low-level noise. By mechanically eliminating neutral noise, the need for helium use in the mass spectrometer is eliminated, allowing the system to be truly helium-free if desired, reducing laboratory cost and supply pressures. As with a single quadrupole GCMS system, the first quadrupole will eliminate all ions except for the ones with the mass-to-charge ratio of your analyte. However, if a matrix ion of the same mass collutes with your target, a single quadrupole system cannot differentiate the two. With the TSQ8000 triple quadrupole system, these ions can undergo further fragmentation in the collision cell, creating unique ions. The unique ions are then isolated in the third quadrupole, eliminating the potential matrix interference before moving into the dinode multiplier. This allows you to lower detection limits in complex matrices and enables the operator to combine several methods into one. The TSQ8000 instrument software makes it the easiest system to realize the analytical benefits of GC triple quadrupole analysis. Newly introduced with the TSQ8000 system is a new innovative software feature called Auto SRM, which automates the SRM development process to enable you to add your next new compound to your methodology. You can start from scratch, or you can begin with an imported single quadrupole method, and Auto SRM will automatically conduct product ion scans and present your best choices for product ions from which to complete your SRM transition. Once your product ions are selected, Auto SRM can automatically optimize the collision energy for your chosen SRM transitions to within plus or minus 1 electron volt. Uncompromised SRM simplicity, another main advantage of the TSQ8000 system. With the system's innovative Extractobrite ion source, proven reliable hardware design, and user-friendly software design, the TSQ8000 offers uncompromised MS-MS simplicity to maximize the analytical advantages of high-performance GC triple quadrupole technology. To learn more, contact your local sales representative today or visit www.thermoscientific.com/TSQ8000.
The 7000A triple quadrupole GCMS is the first quadrupole MS-MS system designed specifically for the unique requirements of gas chromatography applications. These requirements include enhanced selectivity, consistent low detection limits, and robust day-to-day operation. The typical MS-MS description focuses on the extraction of ions from the source, isolation of the precursor ion in the first quadrupole, dissociation of precursor ion in collision cell, and mass filtering of the product ions in the second quadrupole before detection. But let's return to the ion source to discuss processes that are often overlooked. Even for a high-performance source, ionization efficiency as a percentage of molecules entering the source is very low. This means there are many more neutrals than ions exiting the source, so a thorough description must include analytes neutrals and ions, helium neutrals and ions, column bleed neutrals and ions, and many more neutrals and ions from the matrix at concentrations typically higher than the analyte. To simplify the description, let's start with the analyte molecules and ions. Analyte molecules enter the vacuum source from the GC capillary column and begin bouncing off the hot surfaces of the source. Analyte ions are immediately extracted from the source and focused into the quadrupole mass filter. But what about the non-ionized molecules? The electrical fields within the MS have no influence on these molecules. They follow rapid, random motion until removed by the vacuum pump. Parallel processes are occurring simultaneously for the molecules from the sample matrix, and instrument background like column bleed. The quadrupole analyzer performs the critical task of mass filtering to isolate the analyte's ions from the majority of these ions. Chemical noise often remains after the first quadrupole, but the selectivity of MS-MS removes this final source of interference. Again, we ask, what about the large population of non-ionized molecules? Although the turbopump removes many neutrals quickly, some will randomly diffuse into the quadrupole. At the end of the GC separation, the EI source will be flooded with the highest boiling molecules from the sample matrix. Even in a vacuum, these high boiling molecules can contaminate surfaces in the mass spectrometer. A cool surface will accelerate this contamination process. As we think about the potential for contamination, we must not forget helium. The intense flux, high flow of helium ions helps to burn the high boiling molecules onto the surfaces of the source and the analyzer. The cooler the surfaces, the faster the rate of contamination, and the faster performance is lost. For an LC atmospheric pressure source like ESI, metal quadrupoles at temperatures of 100 degrees Celsius are perfectly adequate and commonly used. But for GCMS-MS analysis, metal surfaces at this temperature will quickly become contaminated. The Agilent 7000A uses a combination of proprietary and patented technologies to avoid contamination problems and ensure robust, high-performance operation. These include an inert source operating at up to 350 degrees Celsius, and quartz quadrupole operating at up to 200 degrees Celsius. With 35 years of MS experience, Agilent built the 7000A around the unique hot quartz analyzer of the MSD, not the cooler metal quadrupole rods used for LC-MS-MS. Before continuing to the collision cell, one more process must be mentioned. An EI source produces a large number of highly energetic metastable helium atoms. These highly energetic atoms follow a random path like any other neutral until removed by the pump. Some will follow a path parallel to the analyzer and have a high probability of traversing the entire analyzer assembly to the HED-EM detector. During the development of the 7000A, Agilent engineers realized a small flow of helium added to the nitrogen collision gas was a very effective way to reduce the transmission of metastable helium through the collision cell. We call this patent-pending solution helium quenching. A comparison of signal-to-noise ratio with and without helium quenching shows the benefit of this technology. Helium quenching has no effect on product ion signal, but the neutral noise component is reduced by a factor of 4. This technical breakthrough means lower limits of detection and quantitation. The 7000A MS-MS, an MS-MS system optimized for gas chromatography. From the classical distribution of ions produced in the inert, high-performance source to the precise isolation of the precursor ion through the path of the hot quartz hyperbolic quadrupole, into the high-pressure hexapole collision cell for efficient precursor dissociation, product ion transmission and simultaneous reduction of metastables with helium quenching, to the final accurate mass analysis in a second hyperbolic quadrupole field before ion collection at the triple-axis detector, the 7000A system has been carefully designed to deliver robust sensitivity and reliable quantitative results. The Agilent 7000A quadrupole GCMS MS system, an MS-MS optimized for trace analysis of your most complex GC samples, the new standard for GCMS MS performance. Agilent Technologies. Our measure is your success.
Some few explanation of the mass spectra of alkanes. In this case, what we're seeing here is the mass spectra of unbranched alkane. Fragmentation always happens from the most simplest fragmentation that can happen. For instance, first lose the methyl group, and then you the methyl group and the ethyl group up until the whole molecule is completely fragmented. For instance, here, if one look at if the molecular weight of this compound is 72, molecular weight of 72, you'll see a molecular weight of 72, and then if you lose CH3, which is minus 15, you'll get to 27, and then from there you lose the CH2, CH3, and you get to the 43. So if once you see at 43, the silicon which has more stable carbon will be more abundant. So what that happens is that if you look at if you lose CH3 and CH2, what's left in the from the CH3, CH2, and CH2, the positive ion will be at that CH2 plus there from the CH3. So there's more than 2-3 carbons where the carbocation ion can be the positive ion can be stabilized and rearranged. That is why what the carbocation ion means, and that's why that's why the highest peak will be coming from in that molecule because of the stability of because of more places where the positive ion can be stabilized. That's why they call it a carbocation ion. Now, also, if one look now at the mass spectra of the branched alkane, in this case 2-methylpentane, with a molecular weight of 86, so the fragmentation will happen because where the simplest fragmentation always happens where the CH3 will be lost on the right hand side of the molecule. In this case, you lose CH3, and then 86 minus 15 give us 71. It's always important to remember that the one that you lose, in this case the CH3, it's lost as a hydra. So that you won't see a tick for that on the spectra, because the one that you lost is lost as a hydra. You only see a peak of the positive that has been left. One case you'll see a tick at 71, because there it's from the CH3, CH and the CH2 and the CH2. That's where the positive will be. So you'll see a peak for that. Now, if you look at that CH2 again, which is another 14, so eventually from 71 minus 14 we get to 57. So that will come from CH3, CH, and a CH2. That's where the positive will. And then we lose again that CH2. Now we come with what we call a carbocation ion, because what's going to be left is CH3, CH, and the positive ion will be on the CH. Now you'll see now, that's where the 43 comes in. You'll see now that the most intense line or most intense peak in there, because of the carbocation ion. That's what we call a base peak, and the base peak comes from the most stable carbocation ion, because of the stabilization of the positive ion in that molecule. And then from there on, it will be fragmented until it's completely fragmented. Because if we come back to that positive ion, which I mentioned earlier, see, the positive ion can move from the CH, where it's not stable, it can go into the CH3. And when you go to the CH3, it will be CH3 and the plus, and then you can have a double bond forming maybe in the second CH3, then that will be stable, and you can also move around to another CH3. That's why they call it a carbocation. There's more than one place where it can be stabilized. When one look at molecules with heteroatoms, your heteroatoms are compounds like your bromine. On the molecular weight, you'll see an M+2. M+2 is equal to the M+2. It means you'll see the molecular weight plus 2 more ions, and they will be of equal height. You'll see when you do an example or two of fragmentation. And also, if chlorine is present, you'll see M+2 is 1/3 of M+2. The M+ will be higher, will slightly higher than the plus, because of the chlorine. It becomes easier when one look at the spectra when it comes to the next slide. If one look at the spectra of mass spectra of this molecule with a sulfur compound that had a compound sulfur, you'll see the molecular weight is 73 of this whole molecule after losing the hydride, of course. You'll see there's two after that intense 76 M+. You'll see there's two small ticks there on the right of that. That's where the M+2 is there, which M+2 is larger than usual. Now you will lose. Now let's go to the problem. If you lose the CH3 there, we have 73 minus 15, and then it will give us 61. Now, if you look at that molecule, at the spectra there, you can see already the most intense line there is already already now onto the carbocation. Because why? If you lose the CH3 on the left there, you'll see we're left with CH2 and the sulfur and the CH3. So the positive ion will first be on the CH2 after losing the CH3 on the left, and then that positive ion can be stabilized by the sulfur. It can also be stabilized by the CH3 that's left on the right. So that's why it's the most intense peak there in this example. As I said earlier, it's important to understand that fragmentation won't happen on the right from the right. It's first going to happen on the left, because that's what the most simplest it can be. Because of the sulfur make it difficult for the molecule to start fragmenting one side. It has to fragment further away from the heteroatom. Now let's look at the fragmentation where there's chlorine in this molecule. This molecule, the chlorine, the CH3 that will be lost first. Before we do the fragmentation, let's look at the molecular ion, the M+. Because you've got chlorine, it's got two groups. You've got the chlorine 35 and chlorine 37. The chlorine 35 is the one that will give you the molecular ion, for instance, in this case, the molecular ion of 78. Now you'll see there's two small other peaks, of which the very last peak or the last tick is at 80. It's because of the M+2, because of the atom 37. But the most important one is from the atom 35. So now you see, if we lose that CH3 from that from that 78, we will be left with 63, and then from there on you will see the carbocation will be on the C+, and your most the base peak will be at 43 there, after we have lost the chlorine, and then because what's left here, it's the methyl, the 2-methyl group, and the CH. That's where the positive ion will be stabilized. When one look at this chromatogram here, it was for the analysis of acrylamide in potato chips using acrylamide D3 as an internal standard, you'll see it. Okay, if you look at the first peak on the left, it looks like it's one peak, but I can show you that it's 2 peaks there, and also at 12.7, it's also 2 peaks there. We'll see with the next slide when we sort of monitor now the different ions from the unlabeled and the labeled. Why I said it's 2 peaks. As mentioned earlier in the previous slide, if you look at the 11.77 minute and the 11.780 minute, you'll see at the top one, it might not be clear, but it's 56. It's iron 56, and the other below that is iron 58, and then you've got iron 71, and also iron 74. It's because of the deuterium labeled and unlabeled. The 55 at the top is from the unlabeled, and the 58 is from the labeled D3. So sometimes when one is doing analysis on the GCMS using labeled and unlabeled, you won't always separate the labeled from the unlabeled. That is why if one is using deuterium labeled internal standard, especially if of the same analog, using ECD or NPD, it's not going to work because you're not going to separate that peak. So it works in very handy when we're using MS or you do operating in an MS here. Also at the bottom here, iron 71 will be from the unlabeled, and the iron 74 will be from the labeled. As you can see, they share the same retention time of that. So of which the iron 55 might be a qualifier, and then iron 71 might be a quantifier of the unlabeled acrylamide, and then 58 might be the qualifier for the deuterium labeled, and then 74 the quantifier for the unlabeled. So one can choose which one to use, or you can use both, and then you use the ratio. But what I normally do, for instance, I will calibrate and quantify with both the qualifier and the quantifier, and I just add the results, and I get the average. This slide here, it's a continuation of the previous slide where I was explaining to you the ions from the unlabeled and the ions from the labeled. As you can see, 55 and 71 will be from the unlabeled, and then 58 and 74 from the labeled. Just a further explanation after I've blown out the spectra from the previous one. Right here it shows an example of using a single quad in the MS mode, and also comparing with the time of flight and the MS in terms of when using the triple quad. The MS slide is going to come after this one, but if you look at these 3 slides, look at the matrix, how it looks like. There's a lot of interferences. The peak of interest is at 23.76 a minute. I mean, look how that peak look like from QuEChERS in hopes, and then you'll see when you go to the MS how it gets filtered, how better it looks like, and then you'll see there's just an explanation or how understanding of how MS work. There will be 2 slides, one from geometrics and one from thermo, or the 2 different triple quads. They explain how MS it's done, how it's performed. And then also with the time of flight, even if it's more advantageous than a single quad, but it still do not distinguish a target mass from the background. Now look at this now spectra of this chromatogram here that we've got here of the same compound using the SIM and the SRM or MRM. How this peak now, the chromatogram looks much better compared to the one previously. Triple quad MS in an MRM mode. Look at the top one. It says the matrix cut from the chromatogram, and it provides lower detection limits, so you can go lower with the MS than you would with the SIM. If several you with the SIM, you were betting to see, for instance, maybe 10 ppt. I'm making an example. When you go to the MS, you might even go to as lower than 1 ppt, which is already 10 times higher than that. You can even go maybe to 2.1 ppt, which is sub trace. So there's the advantage of using an MS. The other advantage that you have with MS, the chances of you reporting an interference are lower than when you're doing SIM. But the reason being that because you might have a compound that fragment two compounds, and your compound and the interfering compound, they might fragment to the same daughter, but their daughters will separate, will fragment differently. So that's where the advantage is. I always say, if say as you're working in a forensic lab and you report the results which were run on the SIM and the MS, your results might not stand if you have to appear in court, because the chance of you reporting the single reporting the interference are higher when using the SIM than when using MS. And also bearing in mind that MS, you take the parent eye and you can fragment it into its daughters, and the daughters can be fragmented into their daughters, and so on, using a certain collision energy. So your chances of reporting an interference are minimized when using a triple quad. This slide here explains the previous slides about the quinoxyphene for the SIM and MS for the single quad SIM, and for the triple quad MS. It explains that, so it's self-explanatory. The remaining slides from this one where we are now, I think it's 45 up until 48. It's some few troubleshooting guide for you when you're experiencing problem. For instance, if you've got a leak, how to check the leak on the MSD, and you might have to separate the taken in part. I always say, for instance, if you've got an air leak on an instrument, it's not always a good thing to start on the MS. Always start from your sample introduction. For instance, you might find that maybe the scepter has got the whole scepter is weak, so you'll have to replace that scepter, put in a new scepter, and then check again, and then check the air leak again, and then you find that the air leak is gone. Or check the O-ring that's sitting on the liner inside the on the injector. Maybe that O-ring needs to be replaced, and then also check on the fittings and all the connections. So that's where you start. And then if you've checked and you still can't find the air leak, then your leak, it might be maybe because the transfer line, the ferrule transfer line, maybe it's cracked. It needs to be replaced. And then, or maybe you might find that there's a leak coming from your MSD on the side, the O-ring on the side of the MSD needs to be replaced, or maybe your vent valve is open, or maybe the O-ring on the vent valve needs to be replaced. So yeah, you can go through all the slides, and then they're self-explanatory. And if you've got questions, obviously you're more than welcome to drop me an email, and then I will answer to this to all those questions via email. We have come to the end of the this training, and thank you for your attention, and thank you for taking part. Yeah, if you've got questions, you're more than welcome to email me the question. What I will do is I will compile the questions as they come in, and I'll answer them in another presentation form. And I hope this was helpful for you. Yeah, it's not always easy to do online training when you're not seeing the person, and sometimes it becomes much easier if one explains looking at the people that are taking part. So must also say this was a learning process. It was the first time that we're doing it like this, and then let's hope and pray that the things will be differently in the new year, when we'll have got the COVID under control, and then we can see each other face to face. There's a lot that one can learn, because it was only scratch the surface of what can do, and because it's easier when you see the instrument in front of you, and then also you ask questions better, and then you understand it even better. But I think I hope I've tried my best under this condition to try and introduce to you. As I said, it's not easy if you're not seeing the people, and it's my first time presenting like this. So criticism is welcome, suggestions are welcome, because you can only improve on that. And then, yeah, thank you very much. Cheers, bye-bye.